Hello, we are DAM Robotics from Oregon State University, and we are proud to present that we are ready for the 2026 University Rover Challenge. This year, we focused on updating our past rover while also building on designs we showcased at last year's URC competition.
This year, we are continuing to reuse our chassis, drivetrain, and suspension systems from URC 2025, which have proven themselves to be extremely effective at going over rough terrain while keeping a low weight and center of mass. A strain gauge monitoring system has been developed for recording chassis forces and impacts at URC 2026, which will be used to inform a future chassis redesign.
A new 3-axis gimbal was incorporated for improved reconnaissance and navigational abilities. Feedback from an IMU was used to create an active stabilization system meant to reduce tremble, provide a steady video feed, and increase video compression.
This year, a ground-up communications overhaul is being performed based on our experience at CIRC 2025. On the rover side, we are implementing a telescoping mast with raised, lower-gain, omnidirectional dipole antennas. On the ground station side, we have designed a GPS-based targeting platform, allowing us to continuously focus our new high-gain ground station antennas towards our rover, improving long-range communications. A supporting software stack has been developed for collecting data, mapping communications performance, and adjusting parameters in real time. Various 2.4 GHz and 900 MHz radio and antenna combinations have been empirically tested, and a dual-band system has been developed for improved communication in non-line-of-sight situations.
Utilizing the NVIDIA GStreamer H.265 encoding client, we are able to send highly compressed and lossless data directly from the rover back to the ground stations, being able to sustain up to 5 video feeds at once. Utilizing Unity for our front end and ROS2 and GStreamer for our telemetry and video feeds on the rover, we are able to maintain good communication and intelligent feedback throughout the entirety of the tasks.
Previously, we've been able to support 2 simultaneous video feeds over USB. To increase driver awareness, we're installing a USB PCIe converter board to support up to 8 more simultaneous camera feeds. An example of 4 is shown here. Currently, we are adding an additional 3 peripheral 140-degree FOV cameras to provide 360-degree visibility.
Using publicly available datasets, we trained a YOLO model to be able to detect all of the game objects at the competition. Pairing this with our camera muxing node, we are able to stream multiple cameras to this model, greatly reducing memory performance. Using RTAB to map our surroundings with our Intel RealSense D455 depth camera, we are able to obtain highly accurate point cloud data of our surrounding area and save it to a local and global map with odometry offsets from extended Kalman filters. Utilizing RTK corrections from the ground station, we are able to build custom missions with waypoints and desired objects to look for, and we are able to follow these paths accurately using ROS2's Nav2 stack built on RTAB mappings.
We have designed a core drill that is able to extract and store samples of dirt from up to 10 centimeters in the ground. Our drill is enclosed by a steel tube that protects the mechanism and keeps dirt contained in the drill for a collection in a cache. This drill is mounted to a linear actuator that drives the vertical motion of the drill. The drill is then capped by a spring-loaded mechanism to prevent dirt from spilling out of the collection chamber. To collect topsoil, we will be using a brush rotated by a motor and a pulley which will drive the dirt into a bucket. This is on a 4-bar linkage. The linkage will move the bucket upwards where the soil will be poured into a collection device for chemical biosignature assays to be run.
Our life detection system uses a pump and valve setup that transfers a soil solution into preloaded chemical tests. We are using Benedict's solution to detect reducing sugars, which are produced by plants, and anhydride to detect amino acids, both which are important indicators of life or prior presences of life. A camera feed views these reactions through a graphical representation of the RGB intensities, identifying color changes. This can be blue to green or red for Benedict's test, and a deep purple result for an anhydride.
Our rover operates a 6-degree of freedom arm mounted to the quick disconnect on the front of the rover. The arm was built in 2024 and is currently being fitted with a new Ethernet slip ring to maintain continuous rotation of the gripper with an in-hand D405 RealSense depth camera. Each joint is driven by a brushless DC motor with harmonic gearbox reduction to provide high torque and low backlash. Motors are controlled by an ODrive S1 motor controller using CAN bus communications for commands and feedback. Move It 2 is used to control the arm in joint-by-joint, servo, and pose modes. These control modes allow the operator to efficiently move the arm around the reachable workspace. Poses are able to be saved on the fly to go back to previously reached positions. The arm has been measured to have a 5mm positional repeatability when moving between 2 poses and can lift 5 kilograms at full extension. The arm is able to autonomously type through localizing to the keyboard and moving through a set of predefined poses.
We will be using a drone for the delivery task to assist the rover in the field with its aerial camera feed and signal repeater systems. The camera is attached to a single servo to control the pitch of the camera for better visibility during flight. The drone is carrying a radio system that receives and repeats the signal to the rover. This allows us to drive the rover out further from the ground station, extending our operating range.
Our team has been working hard this year in preparation for URC 2026, and we are excited to see what competition has in store. Thank you.